Hi, my name is Jose Rojas, and this is my organic synthesis journal presentation on the preparation of highly substituted pyridines via Diels-Alder reactions of vinyl alanines and tosylcyanide. So, on a scale on optimization, this experiment is very expensive. Um, on a scale based solely just what is based on in the paper, it is able to run safely. Anything bigger than that would be unsafe for our environment, unsafe for us, and just hazardous in general. And the chemicals and reagents used in this experiment are very expensive and they're used very scarcely. The commenters actually, with the authors in my journal, they didn't really make any contributions. Well, they didn't make that many comments, they made contributions. Most of the contributions came in through pictures in the article, thin layer chromatography. They were just trying to prove that the authors were doing the right stuff. They also specified that they had the same materials and that their reactions underwent the same conditions that theirs did. They made no comments on any of the matter or the procedure that they did. So our reaction apparatus is right here. Um, uh, we have a three necked round bottom flask. We have a separatory funnel here. We have some argon inlet needles right here that are used. There's a magnetic stir here that you will see in the next slide, as well as rubber septums to stop anything from coming out while it's being added. Here is the round bottom flask with our magnetic stir and some starting material already added. It is the third picture. Sorry, I'm trying to go backwards. It is the third picture. So here our reagent that we are focusing on is phenylpropanaldehyde, which is purified by short path distillation, if I'm correct, at 200 degrees Celsius. And another two reagents that are used in the other reactions that are in this experiment are lithium bromide, and they were dried in a sand bath at 200 degrees, and tetrahydrofuran, which is purified by petrofiltration. So the reaction procedure actually is very simple. Um, you have a 500 milliliter three-neck round bottom flask that is equipped with some Teflon, with a oval magnetic stir bar, some argon inlet adapters, a rubber septum, and a thermocoupler probe. Is fitted with all that stuff. It is then the reaction is then filled with some ethanol cyclohexene. THF is then added, and then it is put into a dry ice isotone bath that is set at negative 78 degrees Celsius internally. Then N-butyllithium is then added to create the reaction. A 50 milliliter pear-shaped flask is then fitted with a rubber septum and added with an argon inlet leader with the phenylpropanaldehyde to slowly, which is placed as well in the dry isotone bath to slowly put some phenylpropanaldehyde into the first three-necked flask. Once it reaches after 30 minutes, it is removed from that. A pale yellow solution is allowed to warm to room temperature. It is then added with some acids so that it can be washed, and then it is let dry at room temperature, and you get a powdery substance. The purification of this product was actually purified through rotary evaporation at 20 degrees Celsius. Um, We know that it is a pure product simply based on that the authors have various methods to make sure that they have the right materials. These included thin layer chromatography, carbon spectra NMR, hydrogen spectra NMR, and mass spec. The experiment, they did not list too many hazardous concerns. The only hazardous material there is the flammable butyl lithium, the fumes from the cyclohexene, the ethanol cyclohexene, all of the cyclohexenes. That's why you work in a fume hood, so that you make sure that does not go into your lungs. So the synthesis could not be run in our lab. It's too expensive. There's too many materials that we do not have, too many flasks, too many glassware that we do not have, too much reagents that we do not have that are too expensive. And overall, the synthesis is hard to occur as well. Luckily for them, it worked out, but they got a very low percent yield. So my mechanism for this one is predicted as that this butyl lithium, since it's added with the ethanol cyclohexene, this carbon here becomes negative, and this is bonded with this lithium that's positive, right? And then this carbon, because of this phenyl group, right, or because of this group right here, this alcohol group, this carbon becomes delta positive since this is taking all the negativity away from it. So this right here bonds to this carbon and kicks this lithium off and causes this bond to occur. And then this bond right here breaks. Water is created as a byproduct, since there's a 73% chance. Water is created as a byproduct here. And this triple bond right here splits into radicals. And it becomes one electron holding two double bonds. That is what I believe is the mechanism. The authors of this journal all have some sort of bachelor's degree in science and chemical engineering, some of them in chemistry, some of them from Cornell, from high institutions. All the authors had some shared experience and had shared the same idea to create this synthesis to try and bring it to life. That was my organic synthesis journal presentation. Thank you very much.